Hello, I am Doug Montgomery, your instructor for our experimental design courses. Hello to all of you and welcome you back to our monthly fireside chat for September. For those of you that are newer either to the courses or to the ideas of the fireside chat, this is something that we do monthly. We have a guest speaker that presents interesting topics about experimental design. We always have some time at the end for questions and answers. This is a great time for you to ask questions, and they can either be about the guest presentation or they can be something about the material in any of the Coursera courses. Or if you have a question that's specific to a situation that you're trying to deal with, we'd be glad to try to address those kinds of questions as well. For those of you that are on the Coursera courses, these fireside chats are recorded and they are posted in the resources tab of your course. And I really encourage you to scroll through those and look at them, because there's a lot of really fascinating topics that are discussed here, and the guests that I've convinced to come and do this are people that are really the experts in the area. And I think this is our 38th fireside chat, so there's a lot of material out there that you can take advantage of. A couple of quick reminders. Please keep your microphones muted, your cameras off, so that we don't get any extraneous noise or things like that disrupt the presentation. If you have a question for either me or a guest, please submit that question using the chat function on your Zoom menu. And you don't have to wait until the Q&A starts. You can start putting in your question anytime during the session. If your question doesn't get answered during this time, we'll respond to it in Coursera for those people that are enrolled. Okay, so that's sort of the background information on how we're going to run this. I'm pleased to introduce our guest today, Dr. Robert Gramacy. Bobby is professor of statistics at Virginia Tech. He's a fellow of the American Statistical Association. He is currently the editor-in-chief at Technometrics, which is one of our major statistics journals. That is an ASA, ASQ journal. As a journal editor myself, I'm going to start off by expressing sympathy to Bobby because it's a hard job. He has served as chair of the ASA's Uncertainty Quantification Interest Group. He's been president of the ASA section on physical and engineering sciences, and he's treasurer for the International Society of Bayesian Analysis. Bobby's research work focuses mainly on surrogate modeling, uncertainty quantification, Bayesian inference, and statistical computing. And I'm really delighted that he was willing to take time out of his schedule, which is, I'm sure, super busy, to spend some time with us today. Thank you, Bobby.
Thanks very much, Doug, for the very kind introduction and for the invitation. I'm delighted to speak with your students today. So I'll try sharing my screen. Okay, so I think you should be able to see my slides. And I'm going to talk to you today about Gaussian processes.
I can see your slide just fine, I think.
Okay, great. So I work on a number of things. Doug listed a few of them. I think the thing that I work most on and that I'm most well known for is called surrogate modeling, or the design and analysis of computer simulation experiments. Simulation with a computer, or you could call it virtualization, is common whenever the physical experiment that you wish you could do is not possible for some reason or another. My favorite example of this that many people will be aware of comes from epidemiology. You can't just make people sick and then watch them make their friends sick. That's unethical. It may be an experiment that you wish you could do because If you could do it, you might be able to entertain interventions like vaccination strategies or quarantining strategies, but you just can't do that experiment. But you can virtualize it. You can create a social network that mimics the social network of a school or of a small town, and you can specify rules about how people interact with one another in their network and watch how a disease, for example, COVID, propagates through the population, and then entertain intervention strategies to stop the epidemic. I'm not going to talk to you about epidemiology today, but I do want to show you an application that we worked on for aircraft design, which is a similar situation. You cannot just build a bunch of different aircraft wings and stick them on airplanes and fly them at 35,000 feet in order to discover whether or not that wing design has a safe lift over drag ratio, for example. That's the particular application we're interested in. You have to virtualize that for all sorts of reasons. Cost is one, ethics may be another. And there are lots of good computer-aided design toolkits that allow you to entertain this kind of virtualization or this computer experiment. We're going to use a piece of software called SU2 that takes care of that virtualization that will allow us to input parameters that describe the shapes of a wing and that describe the environment that it's flying in terms of its speed and its angle of attack and so on. And as output, we get many things, many different forces on the aircraft, but we're going to study the lift over drag ratio. And we have interest in finding safe operating conditions that are specified through this lift over drag ratio. The software that runs these simulations is relatively fast, but it's not instantaneous. It takes about 1 core hour. So that's 1 hour of 1 core of your computer's processing power to entertain one of the input combinations that specify the wing shape parameters and its flying environment. So because computing resources are not free, it makes sense to plan a campaign of runs. So that's to develop an experimental design and use a model of the virtualization through the input and output pairs that you've collected through your experimental design and your simulation campaign. And in my world, that model, which is really a meta model because the statistical model is going to model the virtualization, which is modeling the real world, we call that meta model a surrogate because ideally a good surrogate would, at new inputs where you haven't run your computer simulation, give you an accurate prediction of what the simulation would output, and with good uncertainty quantification, and hopefully do it quickly so that you can do things with the surrogate that you wouldn't have been able to do with the original computer simulation itself. So that's kind of the framework that I'm working in. You can see that it involves modeling aspects and design of experiments aspects. So I'm going to tell you about those two things. The first bullet here is about Gaussian processes, which is the title of this presentation. That'll be the modeling component of this presentation. And then I'm going to talk to you about design of experiments. First, I'm going to do kind of a simple but very popular Bayesian optimization sequential design or active learning setup. And then I'm going to pivot back to this aircraft example that I started out with to show you how we would identify safe operating conditions for the design of an aircraft wing. All right, so the first segment is the modeling segment. And this is what I find to be the most interesting. And the design things that come afterward, I wouldn't consider myself to be a design expert, but I think that the kinds of designs that you can do with these special surrogates are fascinating. And I'm going to tell you about those. So first, I'm going to tell you about Gaussian process surrogate modeling. I think that this slide has the biggest conceptual component in it. There's some other slides with the mathematics and interesting results, but for me, this is the most fascinating thing. How can you do with a Gaussian distribution something that at first, if you've never thought about it before, has to do with functions? It's kind of an interesting link. So I'm going to specify an algorithm. a three-step algorithm for generating a random function from a Gaussian distribution. Whenever you see the words Gaussian process, really all that means is from a Gaussian distribution. So I'm going to specify the inputs of my function. Think about just the numbers 1 to 10, or maybe 100 equally spaced x's from 1 to 10. And then I'm going to calculate the pairwise distances between those 100 inputs. So I'm going to get a matrix that's 100 by 100, and the ijth component of it is going to be something to do with distance. The formula here is e to the minus the squared Euclidean distance. So I'm building a matrix. It's going to be a covariance matrix that's inversely related to distance. So I'm going to have a stronger correlation if my inputs xi and xj are close together, and I'm going to have a smaller correlation if they're farther apart. Then I'm going to take that matrix and put it into my favorite multivariate normal random number generator. So I'm going to take a vector of length n that I'll call y as a random realization of this multivariate normal distribution whose covariance matrix is sigma and whose mean is 0. You can use other means, but for the purposes of this presentation, I'm always going to use 0 mean Gaussian processes. Now that three-step algorithm is implemented in that code block below in slightly more than 3 lines of code. I build a matrix of x's that span the sequence from 0 to 10. I calculate distances between those pairs of x's. I exponentiate them, and then I draw from a multivariate normal distribution at the end. This is R code. This presentation is authored in Quarto, which is very similar to R Markdown. So what you see is what you get. The code is actually run, and the results that you see, that might be visuals like plots, or it might be numerical output that is generated by R at the time that the slides were built. So what you see is what you get. In the very final line in the code, line 8 there, I've got the number 3. So I'm actually generating 3 sets of n vectors of y. So I can show you 3 different random functions. And I plotted them for you on the next slide. So each one of these lines of a different type and color are one random realization from a multivariate normal whose distance structure is inversely related, whose covariance structure is inversely related to distance. I can't predict what these functions will look like. I don't know whether they'll start by going up and then go down, or start by going down and then go up, or how many times they'll change direction. I know a few things about them. Since this Gaussian distribution has a variance of 1, my functions are likely to lie between -2 and 2, as you would typically get from a Gaussian distribution with variance 1. But many things are unpredictable about those functions. So this is how to generate from a Gaussian process to generate functions with a distance structure defining the covariance. That's not interesting for modeling. If you're going to model some data, some x, y pairs that come from a function, you need to solve the inverse problem. What random functions could explain the data that I have? So imagine my computer experiment. I vary my different wing parameters, and I run the simulation. So the wing parameters are the x's, and the simulation outputs are the y's. And now I want to know what random function explains that xy relationship. Well, here's a result from Wikipedia. It's actually cribbed, cut and paste verbatim from the Wikipedia page on the multivariate normal distribution. So you could look there if you want to find these, or you can usually find these in the back of many graduate statistics textbooks. And it says the following thing: if you have a random multivariate normal vector y, and you partition it into 2 parts, y1 and y2, and you similarly partition the mean vector and covariance matrix of that distribution, then you can derive the conditional of one part of the partition given the other. And that conditional distribution will also be multivariate normal, and the mean and covariance matrix of that distribution will have a form that's determined by some matrix vector operations. It's actually a linear projection. So here I've given you the formulas for the distribution of y1 given y2, which has a particular mean vector and covariance matrix that you derive by following that linear algebra. So we're going to use that to make a prediction. I'm going to condition on some example data, some XY pairs, and develop the predictive distribution for some testing locations where I don't know what the outputs are. So specifically, I choose some inputs, squiggly X, where I want to make a prediction, where I don't know what the Ys are. You could call that your testing set. And then I have a training data set of XY pairs, and I want to develop the conditional distribution of the testing set given the training set. And I can do that by following that Wikipedia conditioning rule and get a formula for what the mean and covariance of that Gaussian distribution would look like. And those formulas are on the center of the slide. This is, I think, a very powerful result that I'll demonstrate for you in a moment. These are called the Kriging equations in spatial statistics. So actually, mining scientists came up with this in order to predict where they would find gold ore, given samples of where they have collected gold ore before. But now we use them in computer experiments. They all have all sorts of nice properties. They are the best in a certain sense at giving unbiased predictions, but I'm not going to go through those properties with you. I'm just going to show you how it works. So here is a real experiment, but it's a real simple one. Suppose that I had some data about a process of X's and Y's. You can see on line 3 of this code that the true function is sine of X. So I observe sine of X at 8 equally spaced locations between 0 and 2 pi. That represents the simulations that I did in my computer experiment. And I want to see if I can predict what the output y is as a function of x anywhere across that 0 to 2 pi range, just based on the 8 example data points that I collected. So I need to calculate distances, and I need to exponentiate them to invert those distances. And then I need to create a testing grid. So I make a dense testing grid of length 100 over the range of those inputs. I calculate their distances. And the most important part is at the bottom of the slide, I need to relate the testing to the training data. So I calculate distances between testing and training data and exponentiate those. And now I have all of the ingredients so I can apply that Wikipedia formula. And when I do that, so the 3 lines at the top of this slide is doing that linear algebra to develop the mean vector and covariance matrix of the predictive distribution. I can then visualize that predictive distribution many ways. I can show you the mean of that distribution. I can show you the standard deviations and develop predictive intervals for that distribution. And I can draw from that distribution to show you what functions I might get after I condition on those training data. So on this slide, I'm showing you all 3 of those things actually at once. So my training data are the solid dots on the graph. My predictive mean that I get from the Wikipedia result is in solid black. The quantile-based error bars that are 95% error bars are in dashed red. And each one of those gray lines is one random realization from the predictive distribution. So it's one potential function that could explain the data. And if you take the whole cloud of potential functions, all of those gray lines together, you can see how they kind of follow the black line and the dashed red lines. The true simulation, which is sine of x, is shown in blue for reference. But the only information that we have from sine of x are those 8 dots. And you can see that this is an accurate interpolation, and it has good uncertainty quantification properties because it interpolates. It has no uncertainty where we have observations, and it connects the dots well in terms of having greater predictive uncertainty at the midway points between where you have training observations. Sometimes people talk about this as the Gaussian process sausage, because it kind of, the predictive distribution that you get from this conditioning kind of looks like a sausage. So that is that's it in a nutshell. In fact, I'm going to go back and just say one more thing about this slide. The first time I saw this, I was kind of blown away. I can't believe that you can just follow some result you found on Wikipedia and make accurate interpolations of data. And so if you understand these 5 or 6 slides, you understand, I think, 90% of what Gaussian process regression is. There are many ways to kind of complete it and get that last 10%. So I'm going to show you about half of that last 10%. And that extends the framework to have a more complicated notion of Gaussian covariance. In particular, to fine-tune the way that distance is defining covariance in this Gaussian distribution. So I have changed my sigma matrix, which is what the notation I used before, to have a parameter describing its scale. That's the parameter nu. A parameter describing the signal to noise ratio. That parameter is called tau squared on this slide. And then a set of parameters that govern the rate of decay of correlation as a function of distance in each input coordinate separately. So these are parameters in a statistical model, and we can use any of the things you might be familiar with to dial in settings of those parameters. You could use method of moments. You could use cross-validation. You could maximize the likelihood, or you could choose a prior distribution and integrate over posterior uncertainty. I'm going to show you maximizing the likelihood because that's the simplest to describe and to code up, but any of those things that I just mentioned worked. So the likelihood is just the PDF of a Gaussian distribution. So the log likelihood is the log of that PDF. And I can differentiate that log likelihood with respect to the unknowns. Here I've done it with respect to the scale parameter nu, set that equal to 0 and solved for the maximum likelihood estimate of that parameter. And the formula at the bottom of the slide shows you that matrix vector calculation to calculate that MLE. I can then take a profile or concentrated likelihood approach and plug in that estimate, and then take derivatives with respect to the other unknowns. Tau squared and theta are a little more complicated because although you can differentiate the log likelihood with respect to those parameters, setting that equal to 0 and solving is not analytic, which basically means you can't do it with pen and paper. But you can do it numerically, and that is what I have coded up for you on the next slide. So this is a lot of code, and I won't take you line by line through it. Well, it's not a lot of code. It's 25 lines. That's not a tremendous amount, but maybe too much to take you line by line through in a talk like this one. So these 25 lines code up the negative log likelihood at the top and its gradient with respect to all unknowns on the bottom, so that I can put it into my favorite numerical optimizer to dial in settings for those parameters. So I'm going to use that code in the next 2 examples. So here's a second example. I showed you a sine of x earlier. Now suppose I have a 2-dimensional set of inputs x, and my response y follows the formula in line 5 of that first code block. So you can see it's a nonlinear relationship between x and y in those 2 input dimensions. And it's also a noisy relationship because I've added some Gaussian error in the second part of that line. I can put that data, those x's and y's, into an optimization routine with the negative log likelihood and its gradient and ask for it to optimize it, and it will dial in those parameters for me. And then I can use those parameters to follow the Wikipedia equations so that I can make predictions at new locations that I haven't tried before. So here I'm doing that. I'm building the training data quantities that I need for those Wikipedia equations and the testing data quantities and the distances between them. And then I'm following the linear algebra that's on that Wikipedia page with those covariance matrices for the training and testing data. And then I can use those quantities to visualize the predictive mean surface as a function of the 2 inputs. That's what I'm showing you as a perspective plot on the left. And on the right, I have the predicted standard deviation summarizing uncertainty, where the red colors are smaller standard deviations, and the yellow colors are larger standard deviations. And each of those open circles there is the location of one of the training data. So those are the x coordinates of the training data locations. And you can see that my uncertainty is lower near where I have data in red and higher in yellow or white. So that was Gaussian processes in 2 dimensions to make a regression of a nonlinear surface in 2D. Actually, you can go to whatever input dimension you want. All of the code that I've given you already is applicable. You don't need to make any further adaptations. And to demonstrate that to you, I'm going to consider a test problem that's known as the Friedman function. Jerry Friedman's a famous Stanford statistician who's known for many things, but in particular, he's known for a statistical regression method called MARS, which stands for Multivariate Adaptive Regression Splines. And in his paper on MARS, he developed this function, and it's a nice test function of 5 inputs. So I am going to observe this function at 200 randomly spaced input locations in that 5D space. And then I'm going to see if I can predict the function with my Gaussian process at 1,000 testing locations that are also spaced throughout that 5-dimensional input space. So I've extracted those training and testing data in the code, and I've put that training and testing data into the same optimization library with the same negative log likelihood and its gradient. And if you wanted to, you could do the same thing. But if you're interested, there are lots of good libraries out there that will automate this process for you. And I've grabbed one that's familiar to me because I worked on it that's called LAGP that will let you instantiate a Gaussian process object, dial in its hyperparameters by MLE, and then make predictions at new locations. And there's a little demonstration here on the slide that the estimates of the parameters that you get from the code that I gave you in earlier slides and from the library that automates all of it are very similar. And then at the very bottom, I'm making a comparison between the predictions that the Gaussian process provides and to ones that come from Jerry Friedman's MARS method. And I'm evaluating them by root mean squared error, where smaller is better. So I'm getting a smaller error from the Gaussian process than with the MARS algorithm, which tells me that the Gaussian process is more accurate. So that is my very quick overview of Gaussian processes. And now I want to show you how you can use this model in a design of experiments context. I think that the most common way that people do design for computer experiments is sequentially. And in the machine learning community, they have a word for this. They call it active learning. But if you're not a machine learning person, you can think sequential design of computer experiments or just sequential design of experiments. The idea is that you try to create a virtuous cycle between data acquisition and model fitting. You start with some small, maybe uniformly spaced design or space filling design, and you fit your model. It can be any model, but for this talk, I'm going to fit a Gaussian process. And then you use that model fit and some kind of design goal to develop a criteria that allows you to choose the next X coordinate of where you're going to evaluate Y, of where you're going to run your computer simulation. And after you've run it and it comes back, you can augment your data with that new run and you can repeat. And depending on what you're trying to accomplish with your experiment, you might do the choosing part differently. And in machine learning, that choice is called an acquisition criteria. You tailor the acquisition criteria to whatever your learning or prediction goal is. So I'm going to tell you about a class of problems that's really popular in computer experiments, but also in the machine learning world, which is called Bayesian optimization. That's when the goal of the experiment is to optimize some aspect of your unknown function or of your simulation. So you want to know the coordinates x that, in this case, minimize an unknown function that you only get to observe at a finite number of inputs x. If you think about classical response surface modeling, this is very similar to the steepest ascent idea, or even like a ridge analysis idea, where there are similar themes in play. I want to know where my function is optimized. In the Bayesian optimization literature, it's a global optimization problem, whereas in response surface modeling, it's often a local optimization problem. So the important thing is we get to evaluate the function f, but we don't get to see how it's composed. So people call it a black box function. And we don't get to evaluate it very much because evaluating it is expensive to us. Think about the aeronautic simulation where each run of the simulation, which is what f represents on this slide, takes an hour of computing time. So there's a substantial expense to evaluating the function. So a goal on our solver is that it not evaluate the function too much. All right, how would you do that? You could fit a Gaussian process to your training data runs that you have already, and then you could use an acquisition function to tell you where to evaluate the function next. And there are many of these acquisition functions that are popular in the machine learning literature for Bayesian optimization, but the most popular one, I think, is called expected improvement. Expected improvement defines something called the improvement, which is a random variable that measures the amount which you predict through your Gaussian process that a new input's output would be better than the best output that you found so far. So the predicted output is the y of x in the formula at the top of the slide, and the best you have so far is the f min. So improvement is a random variable measuring the random amount that you predict that you could be below the best you have so far. And what do you do with this random variable? You integrate it over its predictive distribution. Integrating a random variable is similar to taking its expectation. In this case, it's identical. And you can get a closed form formula for how much improvement you can expect at a new input location based on the Gaussian process fit to the data that you have already. And it makes sense to choose the next run to maximize this expected improvement. And when you look at this expected improvement function, you can see that it's balancing two things. There's a plus right in the middle, and the left part of the plus is measuring something about your predicted mean. How low do you predict it is? And the right side of the plus is how uncertain you are about that. So it's balancing means and variances, or in the Bayesian optimization literature, they call this balancing exploitation and exploration. Let me illustrate that for you in a classic example. This example comes from the original paper on Bayesian optimization. So they have a small data set of x's and y's. They fit a Gaussian process to that small data set of x's and y's, and then they evaluate the expected improvement on that Gaussian process. And this code here is just using our Gaussian process fits that we introduced earlier and writing expected improvement as an extra layer on top of the predictive distribution. In fact, I like to view expected improvement as a lens through which you view the predictive distribution, through which you view its means and standard deviations. So here's an illustration of the code on those slides. Each one of the filled circles on the plot on the left is one of my XY pairs. Those are the training data locations. The black line is, again, the predictive mean, and the dashed error bars are summarizing the predictive uncertainty. The best, from the perspective of optimization, the best point that I have so far has a y value of -2, and the green dashed line is going through that value. So that represents our improvement threshold, and any amount of the predictive surface, including its uncertainty, that falls below that threshold represents potential for improvement. So I've got potential for improvement near input 2.5 or 3, and I also have potential for improvement near input 7 through 9, looking again at the left-hand surface. And on the right, the expected improvement surface is showing me the same thing, only it's quantifying it very precisely. I have high potential for expected improvement near about 2.5 or near between about 7 and 10. And I can see that if I need to make a decision, if I have to pick one place to sample next, then I want to pick it at about 2.5. And when I choose it at 2.5 and collect the output at that location, I get to augment my data, which will improve my predictive surface and update my lens into the potential for further expected improvement. And you can see now that if I optimize the expected improvement surface on the right, that I would choose an input near about 8.5. And then I would repeat this over and over again. I don't have any more slides on it, but the idea is to create a virtuous cycle through data acquisition and learning. This is a sequential design where the decision about the design is intimately related to the model fit, which is in this case a surrogate model, and to the design goal, which in this case is to minimize the unknown surface through a small number of examples collected as data. So this is maybe my favorite example of design for Gaussian process surrogates. I want to pivot now back to the motivating example. This work is an entire PhD thesis of my student, Annie Booth. And I can't summarize that PhD thesis for you in just a few slides, but I can give you the highlights because they involve themes that are related to the two topics that I just showed you. We use Gaussian processes to fit data obtained from a campaign of runs from a computer simulator for that aircraft wing design, and we use an acquisition criteria to do active learning in order to solve a reliability goal. Okay, so here are the specifics of that experiment. Suppose we wish to identify a contour in the 7-dimensional input space describing the input configurations of these wings and the environments that they're flying in that separates passes from failures. So passes are where the lift over drag ratio is less than 3, and failures are where it's greater than 3. So you can think about this as a safety or efficiency threshold. It actually can be viewed both ways, and I don't want to get into that. One thing that you could do if you wanted to identify this contour that separates passes from failures in this input space is you could run a really big experiment with a space-filling set of inputs. I don't know if you've talked about space-filling design in your design of experiments class, but you can just think randomly put 1,000 X's in this 7-dimensional space. In 7D, that's a very big volume. 1,000 random examples is not very many in a big space like that. But what I'd like you to maybe think about, what are the chances that any of those 1,000 space-filling X's would actually be close to the contour that separates passes from failures. You don't know where that contour is, and you know it's a submanifold. What does that mean? It just means it has lower dimension. The separation is like has zero measure in the 7-dimensional space. So that's my way of trying to convince you that the chances that you would find that contour randomly are very small. But perhaps you can start with a relatively small space-filling experiment and iterate through active learning towards a design that concentrates your runs near that contour and gives you a better view about where that separating manifold is. So how can we do that? I need to develop an acquisition criteria that's tailored to the contour finding goal. So here's how you can do that. You can define the probability of exceeding the threshold. So G is my threshold, that's the number 3. So P of X is the probability that the output Y exceeds the threshold. You could do the same thing with is lower than the threshold, that doesn't matter. So that represents the probability of a failure. And then once you have that, you can calculate that probability analytically, that means in closed form, if your random variable y follows a Gaussian distribution, and it would for a Gaussian process prediction. So I can create a lens through my predictive mean and standard deviation, mu and sigma, that tells me about the classification of my response surface into failures and non-failures. Then I can take that probability and calculate its uncertainty. And the way to calculate uncertainty for a discrete measure, like these probabilities of pass and fail, is through the entropy function. The entropy is a simple function of probabilities, which maps probabilities closer to uniform. In this case, there's two classes, so uniform is 0.5, 0.5. I have higher entropy near probability 0.5 and lower entropy near probability 0 and 1. So this is the lens through which I'm going to look through the predictive distribution, and I'm going to show you what that lens looks like. I can't show you in 7D, that's really hard. So I'm going to use a simpler function in 2D that's called the plateau function, where I've observed this function at 5 training data locations. And what I have on the left is my prediction of that function, along with the true zero contour. In the middle, I have my predictive uncertainty for that response surface. And on the right, I have the lens through entropy of my fail-pass classification, showing me that I need to acquire more runs along that yellow-white ribbon, which just so happens to be very close to where the true contour is. So if I take more data in that region, I should zero in on where my response surface separates passes from failures. We evaluated this virtual cycle on that plateau, but we didn't do it in 2D. We extended it to 5D, and we found that we were indeed able to create a virtuous cycle through these acquisitions with Gaussian processes. In fact, one of the things I'm glossing over here is that we used a fancy kind of Gaussian process that's called a deep Gaussian process. And I'm sure you've all heard of deep neural networks. So deep Gaussian processes are the next evolution of Gaussian processes in the same way that deep neural networks are the next evolution of neural networks. So we were able to get more accurate predictions as we grew our training data set sizes, while at the same time limiting those training data set sizes and doing better than if we just did a static space filling design to start out with. Once we were convinced that it was working in this synthetic toy environment, we applied it on the wing design for the aircraft. We were limited in the number of experiments that we could do and the number of alternatives that we could entertain as benchmarks because of the expense of the simulation, but we found that we were getting very accurate designs with small budgets by fitting our deep Gaussian processes and making acquisitions through entropy. So that's what I wanted to tell you. I'm going to leave you with a couple of resources. If you're interested in more about the reliability experiment and deep Gaussian processes, you can check our papers, which are available from my webpage or more directly through that link. And like I said, that's my student Annie Booth's thesis research. And everything else, all of the fundamentals about Gaussian processes and about design for Gaussian processes and about Bayesian optimization can be found in a book that I wrote. And I'm not trying to sell you a book. You can get this book for free on my webpage. But if you want a hard copy of it, then you have to send money to CRC Press. So again, thank you very much for listening and for the invitation, Doug. Thanks so much.
Thank you, Bobby. This is really a fascinating talk. I really enjoyed it. Do you know that your student Annie has also been a guest on a Fireside Chat?
I didn't know that. Well, you know what? Now you mention it, you might have said that at one point, and I had forgotten it.
Well, I thought maybe she had told you that I had asked her to be a guest, and it was because she gave a talk at I think it might have been the last FTC. And she was a great speaker, And I said, well, gee, you know, I should get her involved on a fireside chat. So just to let you know, you did a good job with that student. Right?
I'm not going to take much credit, Doug, but thanks so much.
Yeah, she's very competent. And I'm kind of fascinated about the airfoil testing because I've been involved in wind tunnel testing of airfoils quite a bit actually. I don't know. Do you know Ray Hill? Who he was a professor at the Air Force Institute of Technology for a long time, and he just retired about a year ago, and he was involved in trying to improve the efficiency with which the Air Force did wind tunnel testing. And I don't know if you know much about how that's done, but it's kind of a nightmare. You have a physical model that you put in the wind tunnel, and you might be interested in changing maybe one or two parameters on the airfoil. You might want to change the spacing of the fences on the front of the wing that they disrupt the airfoil, and you might also change the where they're physically located front to back. And the way they traditionally did these experiments is they would have like 8 or 10 levels for each of these factors, and they would vary them one at a time. So it's a gigantic one factor at a time experiment, and each run in the wind tunnel requires somebody to physically go into the wind tunnel and reconfigure that thing, and then you have to run the equipment, and so you can spend a half a day doing one run, and Ray and I looked into some other ways to do that, and we found that if we could convince the wind tunnel people to use standard response surface designs, which required far fewer runs, that we could produce a model of the response variable, which is typically lift to drag, just like you're looking at here. That was an almost perfect match to the models that they got by using these one factor at a time tests. And it was really eye-opening for the people at the Arnold Test Center that we worked with, and I think we were successful in convincing them that there's a better way to do it. But I just wonder whether the computer in your experience, does the computer modeling then inform some of the wind tunnel testing?
Well, I don't have any experience with that in particular. I've worked on other problems where the goal of the computer experiment is to augment or inform how the physical experiment is conducted. I've worked on a lot of those. I have a whole chapter on that in the book. We call that computer model calibration, but it really is trying to create a synergy between the virtual and the physical world so that they can support each other, so they can help each other where the other one is insufficient.
Yeah. Well, I didn't know much about the wind tunnel testing world until I got into it, but it seemed to me that they were doing their testing based on their aerodynamic understanding of the problem. It would seem that the computer modeling, excuse me, the computer modeling that you're doing would be very useful in informing the folks that actually are designing the wind tunnel tests, and it might even allow them to do some of that more efficiently. I would encourage you, if you want to get in touch with Ray Hill. He retired, but he's still he's still an active faculty member at AFIT, and I think he would be fascinated by what you've done here. And maybe perhaps this might be something that you and Annie might be able to build into a funded research project with Air Force Office of Scientific Research, because it is. I mean, what you and she have done here is something that has great potential to reduce the amount of testing that's going on. And from what I understand about this, from the work that I did with Ray Hill, is that wind tunnel testing has a backlog that stretches into the into the far future. And there are people waiting out there for ages, to get access to the wind tunnel to be able to do their testing. So it's kind of a useful thing. Hopefully, you could, and if you'd like, I would be glad to try to get you in touch with Ray, or
Definitely, I'd appreciate that. I know that I've heard his name before, but I don't think we've met.
Yeah, he's very active in the test community within the DoD. In fact, I have a research project with the DoD. In fact, it's a multi-university project. AFIT is involved. The Naval Postgraduate School has been involved. ASU is involved. In fact, Jeff Vining there at Virginia Tech has been involved in this. And there's like 6 or 7 schools involved in this. And what we've been doing is looking at experimental design strategies for operational testing, which is sort of the final stage. You finally got this thing built, and you've got prototypes that are production articles. And then you take these prototypes and you test them under user conditions, just to make sure that they really work the way they're supposed to. And the experiments are typically very expensive, and they're run in the field with user personnel, and it's just finding the right kind of experimental designs to use and how to analyze them is an ongoing question. I've been doing a lot of work on how optimal designs fit into that framework, and things like non-regular fractions and that sort of thing. So it's been fascinating work. But anyway, you might want to talk to Jeff a little bit about what he's been doing. That would give you a little bit of insight as to how that group works. And I will be glad to try to send an email to Ray Hill and suggest that he get in touch with you and Annie. And maybe there would be a nice collaboration there that would be useful.
You're terrific. Thanks.
Sure, be glad to do it. So are you continuing to work in this area, or are you moving on to something else?
Well, I mean, broadly speaking, yes. I'm going to let Annie do most of the airfoil work. She's continuing the collaboration with the co-author that we work with at Penn State. Okay. I'm trying to let her come out from under my shadow a little bit. But Gaussian processes and Bayesian optimization and active learning are present in all of the research projects that I'm supervising with students at Virginia Tech.
Great. Well, I was very impressed with her. I hope that your other students are just as good.
They're very good. It's hard to compete with Annie, though. Annie was terrific.
Now I'm going to show a selfish side of me right now. Do you have any students that are close to finishing?
I have 2 students that are supposed to finish in May.
Ah, okay. Um, we are allegedly going to be allowed to recruit again this year. We hired quite a few people last year, including 4 new faculty for our IE program. But we really need someone that has the skill set that your students possess.
I know that one of my students, one of those 2 that I mentioned to you, I know that he wants an academic job, so that could be of interest if you do recruit.
Well, if you could tell him that he should take a look at our website and see what kind of positions are available, because I would very much love to have someone that has this skill set on our faculty, because right now we really don't. We really don't. I'm kind of the experimental design guy, and there's a couple of other people that are very good at it too. But we don't have anybody with this specific skill set, and I think it would be a great addition to our core group here. So put in a plug for us if you if you would. Okay.
Will do.
Okay. Okay, well, we are probably drawing close to the end here, and I don't know that we had any questions that popped in. I'm getting the high sign from Nikki that maybe I'm wrong. No, okay, all right, false alarm. Okay, so Bobby, we'll let you have a couple of minutes of your day back, because we're at like 10:29, so it's about time for us to quit anyway. And I do want to thank you again for such a terrific presentation. This is super informative. I learned a lot, and I can see a lot of connections to some other things that I have done that really very insightful. I appreciate you taking time to do this.
Thanks again, Doug. Thanks so much. We'll see
Okay.
you. All right.
Okay. Bye-bye.
Bye.